Today we're going to be talking about solving differential equations by separation of variables. And I kind of referenced this in the other differential equations section, but the difference here is that we're going to have a function in terms of y and a function in terms of x. And we're going to have to separate the variables because the y's can't hang out with the x's. Okay? So what we're going to have is we're going to have dy over f of y equals g of x times dx. Okay? And then we're going to take the integral. This is a topic that we've been finding a lot on the AP, so it's really important that you guys understand how to do this. Okay, first example. So I'm going to separate my variables, so I'm going to divide the y squared over, and I'm going to multiply the dx over. Now I'm going to integrate both sides. I'm in the mood to integrate the right side first today. And then the left side is going to be negative 1 over y. Now you only have to worry about putting in 1c. One big constant is going to take care of all of constants that you could think of. Okay, now we need to find this for when y equals 3 and x equals 0. Okay, so let's plug in. 1 over y is 3, x is 0, so I have negative 1/3 is equal to c. So now we have the equation of negative 1 over y is equal to 1/3 x to the third minus 1/3, or we can think of that as x to the third minus 1 over 3. Now we need to solve for y. So I'm going to multiply by negative 1 first. And then there's a property of proportion that says that I can flip that side, flip this side, and there is our answer. Okay, next one. And this is actually really similar to ones that you're going to be finding on the AP. Okay, so I separate my variables out. So I'm going to have dy over y minus 3 is equal to 3x squared dx. Take your integral. Again, I'm going to do this right side first. We have x to the third plus c. Now the left side is technically a u substitution. Technically, if I make u equal to y minus 3, du is equal to 1 dy. So I'm taking the integral of 1 over u du, which works out to be the ln of y minus 3. If you recognize that 1 over y minus 3, the integral of that is just the ln of y minus 3, that's going to make your life a lot easier. Now let's solve for y. And I want to solve for y right away. And so I'm going to convert this to an exponential, because that's how I break the y out. So e to the x cubed plus c is equal to y minus 3. I chose the positive version because this y is positive. Okay, now here's the tricky part. Ex to the third. When you're adding exponents, that's like multiplying. So really, this is going to become this e to the c. I'm going to make that some new constant k. You can make a new constant c, but that's just some number. I don't even know what it is. Okay, and then I'm going to add 3 to both sides. Okay, now let's solve using our initial conditions. Y is 2, x is 0 plus 3. Well, e to the 0 is 1, so solving for k, we get -1. So we get y is equal to the negative e x to the third plus 3. Now it asks us, indicate the domain for which the solution is valid. So since our derivative has no restrictions on the x, and since this x I can plug in any value, we're valid from -infinity to infinity. In your classwork, you're going to find somewhere you're going to have some domain restrictions, and we'll talk about those in class. Okay, if y changes at a rate, this is important. If y changes at a rate proportional to the amount present, so dy dt, y is changing at a rate. That's a rate proportional, so that's k times y. Okay, so by solving this differential equation, we get this equation right here. K is known as our growth constant if you're greater than 0, and decay if you're less than 0. And that should look somewhat familiar from your previous math classes when you talked about exponential growth and decay. And this is just another way of approaching that concept. This is essentially verifying that concept. So find the solution of the differential equation dy dt is equal to ky, where k is a constant. So let's solve this differential equation. Let's separate our variables out. I divide both sides by y because y has to hang out by the dy, and I multiply the other side by dt. Now I take my integral. I have the ln of y. What's the integral of k dt? Remember, k is a constant. K is a number. That's like saying 5 there. So what's the integral of 5 dt? That's going to be that constant t plus c. Okay, so now what we're going to do is we're going to solve this for y. So e to the kt plus c is equal to y. Or again, we're going to have some new constant. I called my constant big C since I already had a k there. Okay, now we have a few initial conditions. I have to find what this c is. I have to find what the k is. I'm going to plug in this initial condition first because that makes my life easy. At time 0, y is 60. At time 0. So e to the 0 power is 1. That's 1. So c is equal to 60. So now we have a little bit easier of a problem. Now let's use this initial condition. Y is equal to 30 when t is equal to 10. I divide both sides by 60. I use my natural logarithms to solve. Actually, I don't need those absolute values in there. I don't know. I was thinking of my derivatives. ln of 1/2 is equal to 10k. So k is equal to the ln of 1/2 divided by 10, which ends up equaling negative 0.069. Okay, so then lastly, we're looking for our equation. Y equals 60 e to the k t. And that is our solution to our differential equation. That's all we have for today. Please make sure your lesson summary is submitted on time.